So, bottom line is it's a translational research, more or less. I'm humbled to be here, but it probably won't be high-tech, cutting-edge physics. It's more the translation of that. So without too much explanations, what I would like to mention up front is that we have a computer model which is simulating of polarization-sensitive systems, including also the interaction with the living tissue, in this case the retina, human retina, and we're trying to optimize the signals in a way that we don't have too much interference from the optics in the forward and return path when we scan the retina. We are based on a very simple model of any structure that you would like to measure. Let's say in the middle you have what you're measuring, in this case the retina, and you have the forward path and the return path, and they're all represented in our case with Mueller matrices. That's what we prefer to use rather than Jones mechanism, which is complex numbers. But both would work, and we use the Stokes vector representation of the light, go in, reflect it, and return it. It's actually a reflection here. Why is it, are we doing that? Because we are scanning around the fovea, which is the most sensitive part of the retina, and the polarized light, when it, let's say we are illuminating or scanning with polarized light, and by the fringes, the change of polarization state upon reflection depends on the orientation of the nerve fibers in the vicinity of the center of the retina, and that gives us the ability to localize the center of the fovea, and we use that either for eye tracking or, more importantly, for detecting the direction of gaze in eye alignment. This is how an instrument looks like. You have the laser light, near infrared in this case. We have a spinning half-wave plate which spins the polarization plane, and then we have different optical elements. We go here, we go through a scanning motor, back here, toric mirror, go into the eye, go back, and then polarization, we're measuring S1 basically, which is for both eyes, left eye, right eye, and S&P polarization. We consider using the S1 sufficient, not the full Stokes vector, sufficient for detecting the position of the location of the center of the fovea. And we can simulate the forward path with the number of Mueller matrices and the return path also. And we are trying to optimize the whole story. Now, the problem is that many of these these optical elements change the polarization state of light in a very unpleasant way. We have a toric mirror here, we have another, and don't forget that the polarization, change of polarization upon reflection from any surface depends strongly on the angle of incidence. And when you scan here, depending on whether you're here or here, for instance, or in the toric mirror, you have different polarization change. So, with other words, you have spinning elements, like here, the spinning half-wave plate, which we use for a different purpose, and then the scanning motor. And that means that many of these Mueller matrices are actually time-changing, and also depend on the scanning angle, whether you're here or here or here, and that is a problem because it's very difficult to model them. So in other words, we can simulate the whole story. You have the input, forward path, return path, and everything in between is the fundus. Before that, the cornea, retina in, and then the retina out, and cornea out. They all change in time, and they all depend on the patient's properties. So basically, we have a Muller matrix. It doesn't need to be. This is the Muller matrix of a linear retarder, but if it's a normal standard Muller matrix, you have elements here and here, which means a bit of polarization will change. So what's the problem? We want to compensate as much as possible everything which is introduced, change here and here. Here we cannot touch much. We can optimize in a way, but we cannot touch much of that. So yeah, that's what we want to do. We're modeling. In fact, the computer model gives you the output when the eye is looking at the center of a target, and these are the changes in polarity, the frequency powers when we obtain when the eye is looking at the center. This is what we need. This is off-center frequencies, which are not so much used. And everything on top of that, everything depends on the corneal retardance and corneal azimuth. In other words, the fast axis orientation of the cornea, which is also a retardant. And what we do in our model, you remember I mentioned about the two compensators. So what we need is a compensator with a certain azimuth for one of the compensators, let's say compensator 2, which has and that's a compensator 1. We are using the fast axis orientation. So we are using t parameters here, and we are trying to find a place in this cube which gives you the maximum signal. So that's what we measure. And using this, the computer tells us exactly what we need. And this, by the way, has been verified nicely. And that's what you can do for everything. On the other hand, you don't want to have too much standard deviation of the signals. So we want to minimize this, and that's the normalized standard deviation, and you want to maximize this. And that's how we optimize the system. Okay. Now, we can compensate the polarization changes introduced by the system by using standard polarimetric measurement. We have the standard ellipsometric principle. You're introducing using an eigenstate generator, you're introducing usually the 6-degenerate state. You go into the system that you want to measure, whatever it is, and you measure the output. 6 polarization states, you actually need 4. And if you have all 6, then you have an overdetermined systems, which is a little bit better. And you define, by using this, you define what's here. So in this way, you can measure the forward part, and you can measure the return path as well. And that's what we're doing. Why we're doing that? Because we want to, that's polarimetry simple. What we want to do is we want to find a compensator, which could be here or here, so that we can neutralize to a high extent by using a compensator, which is a wave plate usually, with certain retardance and retardation and orientation. You want to compensate as much as possible the aberrations introduced, polarization aberrations introduced by the system itself. And sorry, what we usually have is then when you find when you measure your system, your Muller matrix, then you basically need a compensator which will make this. So the compensator is basically the inverse matrix of the train matrix that you want to basically compensate. It's easy to do that if you have liquid crystal variable retarders. They're a little bit expensive. But that's just an example. You can also use them for measurement, and then once you fine-tune the retardation, then you can put an elliptical retarder, a linear retarder that has a certain retardation, a certain orientation, and then you're all set. One last question that I would like to talk about is this time dependency of the polarization changes introduced by the system. In other words, during the scan, you have different aberrations that depend on this scanning angle. And that's important because if you don't do that, or if you don't consider that, you are running the risk of introducing changes by the system by the optical system that are counted as systems introduced by the human eye. We don't want that. So here is the problem. This is an example of a retinal birefringent scanning system where you have a laser diode, and then you have a scanning system. That's a little bit exaggerated, but this can easily happen. And you go through a system of mirrors, you go into the eye, the signal goes back, same route, and you use the polarization changes, ideally with a polarization analyzer, which is a polarimeter basically. You can only use S1 if you know exactly what you want to measure. And by the way, it is important to know which of those would be most appropriate in a system that's already predefined. In our case, we're using S1. There is a reason for that, and I'll show you why. Rather than using a polarimeter, which costs $6,000, $7,000, $8,000, $10,000, and are not very fast either. So, what we do here is we do a ellipsometric measurement by simply using several scanning angles. In this case, I used four scanning angles. This is solid angle here, of course, 4 positions on that mirror, for instance. And you're measuring with the polarimeter here. That means that you can calculate the Mueller matrix for the whole forward path for that particular ray. If you have 4 rays, then you use 4 Mueller matrices, and then you can tell how much the system as a whole introduces as an aberration. And of course, you can do that for the return path. And that's standard ellipsometric measurement. And when you have, let's say, 4 element Stokes method, then you can do the 6 degenerate states, and then you can measure the Mueller matrix. Same thing as before. And then you can measure the return path in the same way, in the same manner. So you get the 4 Mueller matrices for the forward path and 4 Mueller matrices for return path. No, needless to say, you can do 10 Mueller matrices as much as you want, depending on what precision you want to achieve. But that's the principle. So here are the 4 Mueller matrices, let's say for a scanning angle of 0, 90 degrees, 180 to 70. That's your forward path. And then you can have the return path, another 4. By the way, they're not the same because the calculations are not commutative. You cannot inverse the direction of light and then have the same total Mueller matrix. So you have to do it separately for the forward and for the return path. So that's the interesting story. When you have these are normalized by the first element. This is the change of each and every Mueller matrix element along a scale of 360. So you can see that exactly that's our problem. If these matrices change, then you have a change in the signal, which is introduced precisely by this change of the Mueller matrices, and not by the human eye, not by the object that you're measuring. Same thing for the return path. Changes are not so great, but they could influence the signal, as I saw. For instance, this is the change of a single Miller matrix element. That's the on the first row, the second one, and you can see that you have quite a bit of a change here. And again, row one, that's for the forward.
You have 5 minutes?
Yeah. And for the return path, you have also the same element changing, not much, but like 1%, 1-2%. And if you have a signal which is 5,000 times less than what you send into the eye, this is a low signal. So you really, the signal is low, and the change by the Miller matrix is pretty high. So,
What's happening?
Change your battery. Yeah, it changed.
oh,
That's the old one.
Yeah, hold on.
Next one. Next. This is short.
that's it.
Go to the end now, please.
Yeah, and when you take a look at the four Stokes, four elements of the Stokes vector, you see that all of them change just because you change your position on the scanning surface, and that's what you want to minimize. So that's for the return path. The other one was for the forward path, and then the interesting part of the story is that you have
What's up?
the six polarization states that you use, and you have your changes in the four vectors four elements of the Stokes vector. Now you can tell from this table, you can tell which one is least influenced by the change of polarization. And in that case, for the forward path, you see pretty much that this S1 is best to measure with linear vertical polarization. And then you go to the return path and you say pretty much the same thing. You also see in yellow the ones that you should not use, because in this case they introduce a lot of problems. And finally, you can select here the best polarization. Linear polarization is linear vertical combined with analysis of S1. And in the same way, you can also analyze the depolarization in case you have any. The equation for depolarization is the trace of the Miller matrix, double Miller matrix, and that's the transposed matrix. So it's basically 4 times the upper left element of the Miller matrix. You can use also the equation for depolarization. In other words, you can also tell, using this mechanism, you can tell which input polarization would basically reduce to a minimum the depolarization, if any. And that's the conclusion. Dynamic Miller matrix simulation can help us identify first what input polarization are you using, and then which Stokes vector would be the best.
Perfect, thank you. Any questions? Again, another great presentation and good graphics. Any questions? Okay, if there's no questions, let's adjourn to lunch, and we'll meet you back at
12.